Now we'll study types of discontinuities, and we'll also discuss the reasons when a function can be discontinuous. And we'll try and visualize each situation using graphs. Now basically there are two types of discontinuities. First one is discontinuity of first kind. And this type of discontinuity is also called as removable discontinuity. In this type of discontinuity, this limit extends to a fx. It exists, but it may not be equal to this function value at a, or this fa, it may not be defined. So basically in this case, left hand limit extends to a negative fx will be equal to its right hand limit extends to a positive fx and will be equal to some finite value L, but will not be equal to fa, or this value fa itself may be missing. So in this type, there are further two more classifications. First one is isolated point discontinuity. And second one is missing point discontinuity. Now in isolated point discontinuity, this left hand limit will be equal to this right hand limit, but it will not be equal to this function value fa, which in this case is going to exist, but its value will be different from the value of limits. If we take an example, suppose we have a function x square minus 4 upon x minus 2 when x is unequal to 2, and this is 5 when x is equal to 2. Now if we take this limit x tends to 2fx, it will be this limit x tends to 2 x square minus 4 upon x minus 2, which is 0 upon 0 form. Now we can factorize this. It will be this limit x tends to 2 x minus 2 into x plus 2 upon x minus 2. Now this x minus 2 will cancel, and from direct substitution we'll get the value of limit as 4. And if we look at this f2, value of f2 is 5. So in this case, this limit x tends to 2 fx, it is not equal to value of this function at x equals 2. And if we look at the graph of this function, now this function is basically y equals x square minus 4 upon x minus 2 when x is unequal to 2. So it will be this a plus b into a minus b. So it will be this straight line y equals x plus 2 except when x equals 2. So we can draw this straight line. And this point is x equal to 2. And at 2, its limiting value is 4. And we are given that when x is 2, value of this function is 5. So at 2, value of this function is 5. So in this case, both left hand limit and right hand limit, they approach the value 4, and therefore this limit, it exists, but it is not equal to the value of this function, which is at 5. So in this case, this point at x equal to 2, it is isolated from its neighborhood and therefore it is called as isolated point discontinuity. Now within the framework of discontinuity of first kind, the second type is missing point discontinuity. And in this case, this left hand limit will be equal to this right hand limit, and both of them, they'll exist finitely, but this FA is not defined. And when you have this case, when limit exists finitely but the function is not defined at that point, we say it is a missing point discontinuity. Say for example, fx is sin x upon x when x is unequal to 0. Now we discuss its continuity at x equal to 0. This limit x tends to 0, sin x upon x, it is 0 upon 0 form, which is standard limit. So value of this limit is 1, but at 0 this function is not defined. So in this case, f0 is not defined. Now if we look at the graph of this function, both the limits, left hand limit and right limit, they exist finitely and the value of this limit is 1, but function value at 0 is missing, and therefore this is called as missing point discontinuity. So in discontinuity of first kind, we'll have two situations. Case 1, when the function value, it is isolated from the neighborhood, where left hand limit is equal to right hand limit. And second case, when the value itself at this point is missing, and here also left hand limit and right limit, they are equal. Now the reason it is called as removable discontinuity, because it is possible to make this function continuous by defining a value at fa. So if we define this fa in such a way that this limit it is equal to fa, then this function will become continuous. Now in this case, we know that value of this limit is 4. So if we define this function such that when x is 2, value of this function is 4, in that case this function will become continuous. So what we have actually done is, we are taking this point and we are putting it back in this place to make this function continuous. So now this graph will become a continuous straight line. So rather than taking f2 as 5, we are putting f2 as 4. And in the second case, to make this function continuous, we'll simply define the function value at that point by taking it equal to this limit. So in this case, if we have to make this function sin x upon x continuous, all we need to do is we just need to define f0 and we'll take f0 as 0. We want to define this function as sin x upon x when x is unequal to 0, and we'll take this function as 1 when x is equal to 0, and now this function, it has become continuous. So in both these types, it is possible to define function value at a point which will make this function continuous at that point. Now we'll discuss discontinuity of the second kind. Or irremovable discontinuity. Now, we'll have a discontinuity of second kind or irremovable discontinuity if this limit x tends to a fx itself, it does not exist. or it does not exist finitely. Now here we'll have three cases. Now this first case, both left hand limit and right hand limit, they are finite, L1 and L2, but they are not equal. So these values, they are finite, but values are not equal. In the second case, one or both of left hand limit or right hand limit, it is plus infinite or minus infinite. And this third case, when either or both of these limits, they are oscillating. So these are the three cases when this function fx will be discontinuous at this point A, and this discontinuity will be irremovable discontinuity. Now we'll discuss these three cases separately. This first case, it is called as finite discontinuity. Now in this case, both left hand limit x tends to a negative fx, and this right hand limit x tends to a positive fx, they're going to exist finitely. So we have this value L1 which is finite, and this value L2 which is also finite, but L1 is not equal to L2. Simply value of left hand limit is not equal to value of right hand limit. Then we say it is a finite discontinuity, and at times we'll also call this as jump discontinuity. Say for example, we have this function fx which is 1 upon 1 plus e to the power 1 by x when x is unequal to 0. Now in this case, if you look at its left hand limit, it will be this limit x tends to 0 negative, it is 1 upon 1 plus e to the power 1 by x. Now we let x as 0 minus h, so it will be this limit h tends to 0 positive 1 upon 1 plus e to the power minus 1 by h, and if we put this value h tends to 0, this is e to the power minus infinite, and e to the power minus infinite is 0. So in this case, left hand limit is 1. And for right hand limit, we write limit x tends to 0 positive 1 upon 1 plus e to the power 1 by x. We let x as 0 plus h, so it will be this limit h tends to 0 positive 1 upon 1 plus e to the power 1 upon h. Now this is e to the power infinite, and e to the power infinite is infinite, so it will be this 1 upon infinite, and 1 upon infinite is 0. So in this case, left hand limit, it exists finitely and it is equal to 1. Right hand limit exists finitely and it is equal to 0, but still left hand limit is not equal to right hand limit, and therefore we say this function fx, it has a finite discontinuity or a jump discontinuity at x equals 0. So in this case, this left hand limit, it is equal to 1, and this right hand limit, it is equal to 0. And as we can see in this case, this difference between left hand limit and right hand limit, it is finite, therefore it is called as finite discontinuity. Or there is a jump between the value of limits, and therefore it is called as jump discontinuity. Now in this type of discontinuity, we define value of jump as mod of left hand limit minus right hand limit. So absolute value of this difference between the two limits is called as jump of discontinuity. So in this case, jump of this function fx at x equal to 0, it is equal to mod of 1 minus 0, which is 1. So in this case, jump of discontinuity is 1. So in this case, left hand limit, it is not equal to this right hand limit, and we don't even bother about this function value. So this function will always be discontinuous irrespective of whether f is defined or not defined. Now, in some cases, you'll have this condition where left hand limit, it is not equal to right hand limit, but right hand limit may be equal to this function value at a. So in this case, we'll say this function is discontinuous at a, but we'll say it is right continuous at x equal to a. In the same way, there will be some cases where this left hand limit will not be equal to this right hand limit, but left hand limit, it is equal to this function value at a, and this case still it is discontinuous at x equal to a. But since fa is equal to fa negative, we'll say it is left continuous at x equal to a. Now, one of the simplest example for this case is greatest integer function y equals greatest integer function of x. Now, if you look at the graph of greatest function of x, between 0 and 1, it is 0. Between 1 and 2, it is 1. Between 2 and 3, it is 2. Between -1 and 0, this is -1. If you look at any integer point, say at x equal to 2, then its left hand limit. Now this limit x tends to 2 negative, get a function of x. Now when x is less than 2, its greater function will be 1. So its left hand limit, it is 1. If we look at its right hand limit, it will be this limit x tends to 2 positive, get a function of x. Now when x is greater than 2, get a function of x is 2. So in this case, its right hand limit will be 2. And if we look at f2, this f2 will be greatest in the function of 2, which is simply 2. So in this case, this left hand limit, it is not equal to right hand limit, as left hand limit is 1 and right hand limit is 2, but this right hand limit, it is equal to function value at 2. So in this case, we'll say this function fx, it is discontinuous at 2. So as we can see from the graph, there is a break. So it is discontinuous at x equal to 2, but we'll say it is right continuous at x equal to 2. And by definition, get a function of x, it is right continuous at all the integral points. So in all these cases, it is not possible to make a function continuous, and therefore this type is called as non-removable discontinuity. Now in the discontinuity of second kind, we'll consider the second case when we have infinite discontinuity. And we have an infinite discontinuity if either left hand limit or right hand limit approach plus infinite or minus infinite. Say for example, we have this function fx, which is defined as e to the power x when x is less than or equal to 0, and it is log x when x is greater than 0. Now, if we look at its left hand limit at 0, its left hand limit, which is f0 negative, will be this limit x tends to 0 negative e to the power x, and e to the power 0 is simply 1. So in this case, this left hand limit, it exists finitely and it is equal to 1. But if we look at its right hand limit, f0 positive, it will be this limit x tends to 0 positive log x, and we know that log 0 is minus infinite. So this right hand limit, it approaches minus infinite, and therefore it has an infinite discontinuity. Now if we draw this graph, we know that e to the power x, it is an increasing function. So this is 0 and this is 1. And this graph of log x, it is drawn like this. Now it's 0, this value is 1. So its left hand limit, it is equal to this function value at 0, and it is equal to 1. But its right hand limit, it approaches minus infinite, and therefore this function is discontinuous. As you can see, there's a break in the curve. And in this case, we can see that this jump, it is not finite. So this type of discontinuity is called as infinite discontinuity. And this third type in non-removable discontinuity is oscillatory discontinuities. Now, a function fx, it has an oscillatory discontinuity at x equal to a if LHL or RHL does not exist due to oscillation in the value of function. Say for example, this fx equals sine 1 upon x. Now we know that this limit x tends to 0, sine 1 by x will be this sine infinite. Now sine infinite is not infinite, but it is an oscillating value between minus 1 and plus 1. So at x equal to 0, this function, it will assume all the values between minus 1 and plus 1. And therefore, this limit, it does not exist. And therefore, this function fx, it is discontinuous at x equal to 0. Now, if we look at graph of this function y equals sine 1 upon x, then at x equal to 0, it has oscillating value between minus 1 and plus 1. And therefore, this limit, it does not exist. And we'll say this function fx is discontinuous at x equal to 0. And this type of discontinuity is called as oscillatory discontinuity. So whenever we have a break in the graph of function, we'll say this function is discontinuous at that point x equal to a. And this break, it could be due to an isolated point, or it could be due to a missing point, or it could be due to different but finite limits, or it could be due to infinite limits, or due to oscillatory value. These first two cases, they are called as removable discontinuity, and these three cases, they are called as non-removable discontinuity. And we can work out this discontinuity and types of discontinuity using graphs as well as using analytical methods. Now for this question, we need to find jump of discontinuity. Now if we look at its left hand limit, will be f0 negative, and f0 negative is this limit x tends to 0 negative e to the power greatest in function of x minus e to the power fractional part of x upon e to the power x. Now we let x as 0 minus h
So it will be this limit h tends to 0 positive and will be e to the power greatest net function of minus h minus e to the power fractional part of minus h upon e to the power of minus h. Now greater function of minus h is minus 1. So it will be this limit h tends to 0 positive. So it will be this e to the power minus 1 minus, and fractional part of minus h will be 1 minus h. So it will be e to the power 1 minus h upon e to the power of minus h. Now we'll put h equals 0. It will be this e to the power minus 1 minus e upon 1. So our left hand limit is 1 upon e minus e. Now we'll find its right hand limit. Now for right hand limit, we'll take limit h tends to 0 positive. Now we'll replace x with 0 plus h. So it will be this sine fractional part of h upon fractional part of 10h. Now when h is greater than 0 but less than 1, then fractional part of h is h, and also when h is positive, 10h is also 0 positive. So fractional part of 10h will also be 10h. So it will be simply this limit h tends to 0 sin h upon 10h, and which is 1. So once we have left hand limit and right limit, we can calculate jump of discontinuity, and jump of discontinuity is mod of 1 minus 1 by e minus e, which is 1 plus e minus 1 upon e, and that's your option D. Now here the question is, we are given this function fx, which is limit n tends to infinite x to the power n minus sine x to the power n upon x to the power n plus sine x to the power n when x is greater than 0 and x is unequal to 1, and value of this function at x equals to 1 is 0. Now we need to find its continuity at x equals 1. Now if we look at its left hand limit f1 negative, then will be this limit n tends to infinite. Now this is x to the power n minus sine x to the power n upon x to the power n plus sine x to the power n when x tends to 1 negative. Now x tends to 1 negative means x is less than 1, and if x is less than 1, then as n approaches infinite, x to the power n, it approaches 0. So what we'll do is, we'll write this as limit n tends to infinite when limit x tends to 1 negative 1 minus, now this is sine x to the power n upon x to the power n, and this is 1 plus sine x to the power n upon x to the power n. Now this is 0 upon 0 form, which is standard limit, so it will be 1 minus 1 upon 1 plus 1, and which is 0. So left hand limit for this function is 0. Now we'll find its right hand limit. Now for f1 positive, we can write this as limit n tends to infinite x to the power n minus sine x to the power n upon x to the power n plus sine x to the power n. Now when x is 1 positive, so this limit is x tends to 1 positive. X is greater than 1, that means x to the power n approaches infinite as n approaches infinite. So this is infinity upon infinity form. So what we'll do is we'll divide everything with x to the power n. So it will be this limit x tends to 1 positive, limit n tends to infinite 1 minus sine x to the power n upon x to the power n, and this is 1 plus sine x to the power n upon x to the power n. Now this is not standard limit because sine x to the power n is not 0 but sine infinite, and sine infinite is oscillating value between minus 1 and plus 1 divided by infinite, and finite upon infinite is 0. So this value will be 0 and this value will be 0. So value of its right hand limit is 1. So that means f1 is equal to f1 negative, but it is not equal to f1 positive. So this function is left continuous, but it is discontinuous. And since left hand limit is not equal to right hand limit, it is a non-removable discontinuity, which in this case is a finite discontinuity at x equals 1. That's your option B. Now here the question is, we are given this function fx, which is signum of cos 2x minus 2 sin x plus 3, and we need to find which of the following is true. Now for signum function, we know that if we have any signum gx, then this signum gx will be 1 when gx is greater than 0, 0 at gx equals 0, and will be minus 1 where gx it is less than 0. Now what we'll do is we'll find a range for this function. So we look at cos 2x minus 2 sin x plus 3 when x belongs to 0 to 2 pi. Now since this function is periodic with period 2 pi, we'll work out the solution in one period. The range of this function, it will be, that means this expression is either greater than 0 or it is equal to 0. Now we know that whenever gx is greater than 0, it will be 1, and at 0 it is 0. So what we'll do is we'll find the points where this function is 0. So this is 4 minus 2 sin square x minus 2 sin x equals 0, or we can write this as sin square x plus sin x minus 2 equals 0. Now we factorize this, we can write this as sin x plus 2 into sin x minus 1 equals 0. That is, the value of sin x is 1. It is possible if x is pi by 2. So that means this cos 2x minus 2 sin x plus 3, it is 0 when x is pi by 2, and it is greater than 0 if x lies between 0 to 2 pi except pi by 2. Now we'll talk about this signum function. So this function fx will be 0 at x equals pi by 2, and it will be 1 when x is not equal to pi by 2. Now if we draw graph of this function fx, will be this 0 and then pi by 2, and this is 2 pi. Now this value will be 1 except at pi by 2 this value is 0. And since it is a periodic function, this graph will be repeated like this. Now whenever this function will have a discontinuity, it will have discontinuity at odd multiple of pi by 2. It will be discontinuous at 2n plus 1 pi by 2, and it is an isolated point discontinuity, and that's your option C. Now we have given this function fx when x is unequal to 0 and 0 for x equals 0. Now we need to find continuity of this function at x equals 0. Now it is given that f0 is equal to 0. What we'll do is we'll first find its left hand limit. Now left hand limit will be f0 negative, and will be this limit x tends to 0 negative, and then greatest linear function of fractional part of mod x into e to the power x square, fractional part of greatest linear function of x plus fractional part of x upon e to the power of 1 upon x square minus 1 into signum sin x. Now we know that the greatest integer function of fractional part is always 0. In the same way, fractional part of greater function will also be 0, and this is e to the power 0, which is 1. Now if you look at this denominator, then here in this case it will be e to the power infinite minus 1, which is infinite, and here signum of sine x. Now when x is less than 0, sin x is negative. In this case, signum of sin x will be simply minus 1. So this is 0 upon infinite, and 0 upon infinite is 0. So left hand limit for this function is 0. Now if we find its right hand limit is f 0 positive, and it will be this limit x tends to 0 positive, and again it will be this greatest limit function of fractional part of mod x e to the power x square, fractional part of greatest limit function of x plus fractional part of x upon e to the power 1 upon x square minus 1 into signum of sin x. Now again this is 0, and this is 1. This again is infinite, and when x is positive, sin x is positive, so this is plus 1. So again it will be 0. So for this function, f0 is equal to f0 negative, and it will be equal to f0 positive. So this function is continuous at x equals to 0. Now here we are given this function fx, and it says we need to check continuity of fx at x equals 0. Now if we find left hand limit at 0, it will be this limit x tends to 0 negative x into greatest function of x square log 2 base 1 plus x. Now we know that greatest function of x, it doesn't take a limiting value, it takes exact value. Now when x is 0 negative, then greater function of 0 negative is minus 1, and minus 1 square will be plus 1. So we can write this as limit x tends to 0 negative x, here this value is 1, and we can write log a upon b as ln a upon ln b. So it will be this log 2 upon log 1 plus x. Now this is standard limit 1, so its left hand limit is log 2. Now we'll find its right hand limit. Now f0 positive will be this limit x tends to 0 positive log e to the power x square plus 2 times under root of fractional part of x upon 10 under root x. Now we know that when x is 0 positive, it lies between 0 and 1, and if x lies between 0 and 1, then fractional part of x is simply x. So it will be this limit x tends to 0 positive log e to the power x square plus 2 times under root x upon 10 under root x. Now if we put x as 0, this is log 1 is 0, and 10 0 is 0, so it is 0 upon 0 form, and when it is 0 upon 0 form, we can use L'Hopital's rule. Now if we apply L'Hopital's rule here, we can write this as limit x tends to 0 positive. Now this is 1 upon e to the power x square plus 2 root x into this is e to the power x square into 2x plus 1 upon under root x, and here it will be this secant square under root x 1 upon 2 root x. Now we'll write this as limit x tends to 0 positive 1 upon e to the power x square plus 2 root x, and here this value will be 2 x to the power 3 by 2 into e to the power x square plus 1, and here it will be secant square under root x, and then this under root x will cancel, and we'll take this 2 in the numerator. Now if you put x as 0, it will be this 2 into 1, and here will be this 1 into 1. So this value is 2. So for this function, left hand limit is log 2 and right hand limit is 2. So it has a non-removable discontinuity. So you'll have an irremovable discontinuity at x equals to 0, and that's your option D.